Relativity is a very disconcerting theory. Based on the experimental result that light velocity is independent of the movement state of the observer, this theory has been elaborated starting with this disconcerting experimental observation. Then it turned up in a very strange and mysterious behavior of space and time. For these reasons, few persons in the world shows a good grasp over the relativity phenomena. Misunderstanding and paradox are very frequent. We present here a model of universe and time. That allows us to explain relativity using Epstein diagrams in a geometric elementary way. We build Lorentz equation, not based on experimental data, nor in Einstein postulates, but from a set of non-disconcerting postulates that will define the properties of our model. We will use the model of an eternal block universe. The universe is considered as a stack of instants of time that we identify on a time axis t that goes from -infinity to +infinity. At each point t on the time axis, we can identify the events with an x, y, z coordinate system of a three-dimensional vector space corresponding to our physical space. We will consider only the coordinate x0 and t0 since we will limit our problem to a single spatial dimension, x. In the figure we represent this universe. The points represent events. A horizontal line represents an instant of time for a stationary observer, and a vertical line a position at different times. A spatial axis in black that we take as an example a stationary observer on a line of the train. We can assign a spatial coordinate and a temporal coordinate to this background universe. An observer will observe this universe sliding over it. The observation is carried out with a spatial axis, for example, a meter stick used to measure distance to the origin of coordinates. Postulates. Any line that crosses this universe can support the spatial axis of a reference system that will serve to indicate the spatial coordinate. The time coordinate will be indicated by the time coordinate of the background universe. In the figure we see two frames of reference. A black metro stick that for ease we call the station reference. It is stationary and each point of the meter stick marks the same time. All the clocks are synchronized. The other reference system is inclined. Its watches tick differently from each other. We will call this system the train system. The time they mark is the time marked by the time axis of the universe block as seen in the figure. The spatial coordinates are marked by the meter sticks, from the origin of the coordinates to the point where the event is located. In the figure we show two different events. Until now we have talked about a universe block. This block is the one that is seen from a stationary system, that of the station. A moving reference system such as the train system will see a different block. Seeing it from the train, it will be seen that the train's reference system, the red meter stick, will have clocks at all the points that mark the same time. And you will see that the station system is inclined and their clocks are not synchronized. It is not necessary to understand the problem from the two reference systems, for we will limit ourselves to describing everything from the station system. This is why time is set by the progress towards the future of the station universe. If we saw from the train system, the times would be determined by the block that is seen from the train. Let's clarify. In the figure we represent on the left the universe block as it is. And it will be seen at the station. We see it in purple. Each event can be specified with AX0 and T0. A stationary observer with respect to the station has a meter stick, which we see in black. To the events on this meter stick, we assign the x-coordinate that marks the meter and the temporal coordinate that of the block universe. From the station, we see another meter stick that has an observer from another reference system that we will call red meter stick train system. The events on this meter stick will have a spatial coordinate, the one marked by the red meter, and a temporal coordinate seen from the station, equal to the one marked by the block purple universe. Note that a reference system is only a meter stick. When an event occurs on this meter stick, the spatial coordinate is the reading on this meter stick. The temporal coordinate is the indication for this event in the background universe. On the right we have the symmetrical situation, a universe block seen in a reference system in which the train is stopped. In this system, the red meter stick is the one that has synchronized clocks and sees the black meter stick inclined. Now we will state the way in which we will travel to the future. All reference systems sweep the universe in the direction perpendicular to its present at the speed of light c. This statement is known as Epstein's postulate, or also as Epstein's dogma. With this consideration, the universe seen by the stationary system is a reissue of the background system. Furthermore, the time that all the clocks will show will be time equals vertical distance divided by length velocity. In this figure we can observe the structure of an Epstein diagram. First of all, the black line to the center represents events that occur at the same point on the train line, but these events give different readings of the clocks. A horizontal black line represents the spatial axis of the train's reference system. The points placed on this line are assigned the spatial coordinate that indicates this axis. As the black axis of the station advances in time at the speed of light, then the events located at a height d as the axis passes, the clock will mark the height divided by the speed of light. We also see the meter stick spatial coordinate of the train's reference system in red. Seen from the station, the clocks on this axis are not synchronized, although they would be in the block universe seen from the train. On the left we see two adjacent points. They are at the same point but marking different times. These points represent two observers, one in the train system and one in the station system that are facing each other. The station observer can see the measurement on the train observer's meter stick and the measurement on his watch. Then we can state the following rule. Contiguity rule. Two observers, one on the axis of the station system, at a point on the black axis, x, and another observer at a point on the red axis, of the train, x prime, joined by a vertical line, are in the same physical place, but their clocks show different time. Now we can study the peculiarities of the theory of relativity. 1. Length contraction. The universe model establishes, by the contiguity rule, that a portion of the station's meter stick of length L will be seen from the station of longitude L cosinus phi. In the figure we see two pieces of the train meter stick in blue. In both cases we see that, due to the contiguity rule, the pieces measured from the station are shorter than what they measure on the train meter stick. If you want to understand length dilation well, note that the pieces are measured taking the position of the two ends simultaneously in the station, in the figure at t equals 0. But for train passengers the ends of the pieces are measured at different times. First the measurement of the position of the tip is taken, and then the measurement of the position of the back. For train passengers it is not a good measurement. When one measures the length of a moving object, one must take the position of the two extremes simultaneously, as seen in the figure for the observers at the station, t equals 0. But for the train travelers at those points on the train, the time measurements at the two extremes are different. They are at different heights. What we have just explained can also be demonstrated directly with the Lorentz transformations. Suppose that at t equals 0 in the station a train car occupies the position from x prime equals 0 to x prime equals L in the train system. Equation 2 indicates that the car is seen occupying the position from x equals 0 to x equals L cosinus phi. Seen at the station, the car is contracted. This contraction does not affect the physics of the object in any way. In its reference system, it retains the same length. The contraction is observed in the stationary system because the clocks of two systems that move relative to each other cannot be synchronized. Time dilation. Once time t has passed, the spatial axis of the station will have swept the background universe by an amount ct in the direction of the future of the station. The x-axis will have risen by a distance ct as shown. Also, the train will have traveled a distance ct, but in the direction of the train's red future. For the observers at the station, the train will have advanced only t cosinus phi towards its future. Thus we have t prime equals t cosinus phi. The coordinate of the origin of the train has advanced to the rig a distance x equals t multiplied by c sin phi. Then we recognize that v equals c sinus phi. Then we can write the relativistic factor as the inverse of the cosinus phi, as we see in the figure. To obtain t prime equals t over gamma, while the clock of the station's coordinate origin has passed t, the clock of the train's coordinate origin has advanced t over gamma. This effect is improperly known as time dilation. Moving clocks run more slowly than stationary clocks. But this is seen from the fixed system. But if one takes the universe block as the train sees it, then from the train the clock that runs the slowest is that of the station. Because from this point of view it will be the station that runs towards the future of the train with only one component. Comparison between the measurements of a clock of a stationary system with those of a moving system. In relativity, to compare clocks of two reference systems, it is necessary that they be in the same spatial location. In the figure, we see two events that are in the same spatial location. A vertical line joins them. Rule of the contiguous points. We make the comparison of time between contiguous points with the formula t prime equals t plus h over c. H is equals x prime sinus phi. Then the difference between the adjacent points is t prime minus t equals x prime sinus phi or x tangent phi. The proof from the Lorentz transformations is very simple. Thus we see that the clocks arrive from the left very advanced. But, since they go more slowly as already indicated, they pass through the station and then slowly down. We can say that the train's clocks come from the future of the train, and as its clocks move more slowly than those of the station, they are delayed with respect to the station's system, sinking into the train past. Coordinate transformations. Lorentz transformations. Suppose an event whose coordinates are x, t. From the origin of the station system we must advance a time t and then travel the time axis to point x. The coordinates of the event seen from the train are found in the same way. The origin of the station's spatial coordinates is now in A. The train also evolved by a quantity ct. But for the station system, the train advances only a time t prime equals t cosinus phi, and a distance x equals ct sinus phi equals vt. V is the speed with which the origin of the train's coordinates moves away. That is, the speed of the train. The figure represents all this. The coordinate x prime is located in the spatial location of x. For this we launch a vertical line from x to the intersection with the spatial axis of the train. That is, point D. Then from the figure we see that the coordinate x prime is 0d equals gamma x minus vt. This is the first of the Lorentz transformations. With this same diagram we can calculate the time coordinate t prime at the x prime point of the train, the time marked by the universe block. Equal to the time that the station system would mark at that point is the time t of the event minus the distance ed divided by c. At time t we must subtract the part er equals t minus t cosinus phi, and the part rd equals x prime cosinus phi. We represent the calculation in the figure. Thus we also have the second Lorentz transformation. We have shown here how Epstein's diagrams can be used to develop a model of the universe and time, which illustrates the peculiarities of the special theory of relativity in an elementary way, allowing a good understanding of this theory without falling into paradoxes and misunderstandings. For those interested, you can do the exercise of showing the comparison between the measurement of a fixed clock at the station with the clocks that pass adjacent to it, on the train. Hint: calculate the time shown by the clocks at point B on the train. You will obtain t prime equals t gamma.